All right, let's talk about something that feels like it's pulled straight from a sci-fi movie, using quantum computers to completely upend the world of finance. You hear the hype all the time, right? But what's actually real? We're going to separate the hype from the reality.
So this is the big question, isn't it? Is this for real? You know how Wall Street is, always hunting for that next big advantage. And quantum computing promises a speed up so absolutely massive, it could change, well, everything. But to figure out if it can deliver, we first have to understand what the promise even is.
Okay, so the secret sauce here is this thing called quantum amplitude estimation. Now, don't worry about the math on the screen. Here's the simple version. Imagine you need an answer to be twice as accurate. A normal computer has to work 4 times as hard to get there. It's a grind. But a quantum computer, it only has to work twice as hard. That difference, it's not just big, it's huge. And it's a game changer when you're running millions of super complex financial simulations.
So you can see why this is such a big deal, right? For things like pricing complex stock options, where speed and accuracy are literally the name of the game, this is, well, it's kind of the holy grail. But, and this is a big but, a beautiful theory is one thing. Making it work in the real world, that is a whole different ballgame.
And that's exactly what some researchers decided to do. They said, okay, enough talk, let's put this theory to the test. And they didn't pick some boring old stock, no. They went for something super modern, super relevant, a call option on a tokenized Bitcoin asset. So here's the setup. You've got a Bitcoin token starting at 50 grand. The option is the right to buy it for 55 grand a year from now. Now, using the old school math, we know the correct price for this thing should be just under 15,000 bucks. That's our target. That's the number we're trying to hit. Okay, so this is where the story gets really, really interesting. The researchers run their quantum algorithm, but in a perfect simulation, right? No real-world noise or messiness. And what happens? It works. I mean, it doesn't just kind of work. It works perfectly, like textbook perfect. The physics holds up exactly as it was supposed to. Now, check out this table. You can forget the other columns for a second. Just focus on that last one, reduction. This is incredible. Every single time they add just one more qubit, the error gets cut exactly in half. A perfect 2.00x improvement every single step. It's just so clean. And this right here is the big success story of the experiment. The fundamental theory is rock solid. The quantum mechanics works like a charm. So, if it's all so perfect, what's the problem? Why isn't this running on every trading desk on the planet right now? Right. So we've got this beautiful, flawless result in a simulated world. But now we hit the brick wall. We come to the twist in the story, a huge practical bottleneck that brings this whole thing to a screeching halt in the real world. It's the obvious question, isn't it? If you have an algorithm that works this predictably in theory, why isn't every bank and hedge fund scrambling to use it? Well, the answer comes down to one crucial and frankly devastating type of error. And here it is. Meet the villain of our story, discretization error. It sounds complicated, but the idea is actually pretty simple. See, a quantum computer with just a few qubits can't see the full smooth range of every possible Bitcoin price. So what does it do? It has to chop up that range into a bunch of digital buckets or bins. And that chopping process, that rounding, that's where the error sneaks in. This pixel analogy is the perfect way to think about it. Imagine you're trying to create a super high-res, photorealistic image, but all you have are a few giant, chunky pixels. It doesn't matter how fast your computer is, the final picture is always going to look blocky and wrong because your building blocks themselves just aren't detailed enough. That is exactly what discretization error is doing here. And here's the brutal reality check. A standard classical method has an error of about 120 bucks. Pretty good. The quantum algorithm with 5 qubits, its error bar is, wait for it, over $12,000. Let that sink in. The option itself is only worth about 15 grand. An error that big isn't an error. It's a wild guess. It's completely, utterly unusable. But hang on, this isn't a story about failure. Not at all. In fact, this is where it gets really constructive. Because by identifying this giant, glaring problem, the research gives us something incredibly valuable. A roadmap, a crystal clear blueprint that tells us exactly what needs to happen to make quantum win. And this chart, this is basically the whole story in one picture. This is the roadmap.
On the side, you've got the error. Along the bottom, the number of qubits. It shows us exactly where we are today and exactly where we need to go.
So here's you are here on the map. We're at 5 qubits. And just like we saw, the error is enormous. We're way, way up in the sky, nowhere near the ground where things are actually useful.
So where do we need to be?
Well, to get the error down to 1%, which is what the pros consider the bare minimum, the roadmap tells us we need to get to this spot right here, 12 qubits. That is our target, a clear, quantifiable goal.
So, the million-dollar question, how long is it going to take to close that 7-quadrant gap? Well, based on how fast quantum hardware is improving, the researchers estimate we're about 3 to 5 years away from having machines capable of hitting that target. And really, this single quote from the paper just sums it all up perfectly, doesn't it? Theoretically sound, practically premature. The idea is beautiful. The math works exactly as predicted, but the machines, the actual hardware, they just aren't quite ready for the big leagues yet. And that leaves us with one final critical question. We have the roadmap, we have a timeline. So what does the financial world look like in, say, 5 years, when this technology is no longer premature, but is ready for prime time? That is going to be fascinating to watch. Thanks for joining us.